and today I will talk briefly about part of my PhD research work. And today's topic is to look at design for higher toughness in the area of architecture materials. And what I want to discuss today is a competition between geometric and material heterogeneities, and have two examples to motivate how these two types of heterogeneities are different and how can we use them to design architecture materials for higher toughness. So let me first give a brief introduction of architecture materials. So architecture materials are a class of materials that uses architectures of placing materials geometrically in different areas. And some of these examples are in these nano or micro lattices work that has been doing the past 10 years or so. So this is an extremely lightweight but stiff materials that can withstand itself. That's really early on in 2011. This is published early in Science, and this particular researcher has taken off. And this is some recent work by Carlos Portela and MIT, and they have generated these lattices that can absorb hypersonic impact in this case. So these architect materials can have these very exotic properties, and by also looking at the geometric properties of utilizing stabilities, can use these inclined beams as energy trapping mechanisms. So this video here shows that having these bistable elements, you can actually absorb a lot of energy during impact and protect precious cargo, in this case of a raw egg. So next, I want to move into the areas of my interest is to look at architecture materials, how to design them for high toughness. And a lot of this work that I have been doing is taking inspiration from natural materials. So I want to show a few examples. For example, this is a tensile test of pig skin. And you can see that these skin materials are highly resistant to crack propagation. And also there are ubiquitous examples in marine shells. And this is one of the most prominent examples, which is a nacre, and that you can see they have these brick and mortar structures that are highly resistant to crack propagation. And lastly, I just want to point out another example that are very unique in a sense of natural materials is bamboo. So bamboo actually has the greatest structures in terms of geometric gradient, where the outside of the bamboo structure has these much denser pores compared to the center of the bamboo, which has less dense pores. So if you think about a loading condition of bamboo is always under high bending load, which means that at the outskirts of the bamboo parameters, there'll be higher stress. And this is somewhat the reason where you have these graded structures. So this also alludes to the title of my talk, where you can see that there's a different type of heterogeneities within these natural materials. So, if we can summarize some of these toughening mechanisms that we see in natural materials, it's very nicely summarized in this plot, and going from different scales. And particularly, there are very key toughening mechanisms such as crack deflection or crack twisting. And there's also these crack bridging with multiple micro crackings that happens in these natural materials. And within the field of engineering and materials for toughness, there has been a lot of efforts trying to mimic these mechanisms. So in this case, they have made these artificial nacres using a freeze drying method with aluminum oxide, and you can see that it can create these layer structures to have the crack deflect in these regions. And additionally, this is a work that tries to mimic what's called a Borigan structure, which I'll also talk about in a later portion of the talk, to be a very impact resistant materials using fiber composites. And additionally, with the advance of 3D printing, in this particular examples, they have also mimicked this hierarchical structure that's found in another marine shell that's called a conch shell, which has these high order hierarchy in terms of different lamella structures. And you can see that there's also crack deflecting that can absorb a large amount of impact damage. So I want to now introduce the motivation between material and geometric heterogeneity. So here's a nice example. I think it published recently. Again, this is inspired by Nacre, and just showing this video here, right? Having these Nacre-like structures can be hugely resilient to impact in this case with these Nacre structures. However, right, in this case, which we have just glass, they're very brittle and they break very easily with the impact. However, right, the geometry alone is not enough to activate these mechanisms. In this case, they have to infiltrate these polymeric inner layers to create this structure and to activate these heterogeneities. And this comes to a cost where, right, it's difficult to find materials that are compatible with each other specifically, that can work well, that can bond well with each other to activate the same type of heterogeneities. And additionally, it's very hard to control these interfacial properties between these materials and to find materials that can be tunable. So there are some work that's also very inspiring in the areas of architecture materials. And so in this particular work that's published in Nature in 2019, they have take the inspiration from polycrystalline metals and basically generate these what's called metagrains with different orientations and artificial grain boundaries. And they found that by having these metagrains, you can create a large failure resistance during compression. And additionally, in terms of analogy to metal, they can also generate precipitates instead of metagrains, also shown to generate a larger failure resistance by having these precipitates. So, today my talk will include two topics that work in my PhD to generate tough architecture materials. The first examples, what I will show is a toughening via material heterogeneities. In this case, we'll have what's a PDMS with macrofibers. This is inspired by the work by Professor Chengyang Mo, with having these PDMS with various cross-linking, could generate a matrix that's softer with less cross-linkers in the materials. Like Jun soon talk about that, having less cross-linker will create a material with less stiffness. And the fibers are now with these more cross-linker effectively creating an interface, a well-defined interface with material heterogeneity across the interface. So the first part will be focused on this and looking at the toughness origin in this material. So for the second examples, I will show we can also create tough materials by utilizing geometric heterogeneity. So in this video showing here, there is no multiple material interfaces. The toughness is generated through geometric arrangement of defects that's a result of the 3D printing process called the diffuse deposition model. So first, moving to the first part of the talk, which is to look at these PDMS with macrofibers. And this is really motivated by the fact that silicon elastomer, specifically PDMS, is generally a not very tough materials. So in this video, this is Professor Chengyang Mo's group in the paper of this PDMS elastic dissipator paper. You can see that this crack propagates very fastly through PDMS at a very low stretch and very rapidly. But having these macrofibers here, where the crack is rested at an interface where you have these much softer materials, the softer PDMS with less cross-linking density into a fiber that has more cross-linking density, leading to higher stiffness. And this material is highly resilient to crack fracture and does not even really easily propagate. So by looking at the stress and stretch curve, you can obviously see the advantage of having these composite structures, and it can lead to very, very high critical stretch, right? So I'm not going to give more details about how to measure the toughness, but this critical stretch is very important to the toughness value of these composites. So having a high critical stretch leads to higher toughness. So in the first part of my talk, I'm going to look at mechanistically and the origin of this high critical stretch and why they're having these composite structures with these macrofiber structures can lead to higher critical stretch and eventually leads to very high toughness values of these materials. So look at this in the problem set up. So we will have a bimaterial interface between, we define the materials as Neohooking materials. So for people who are not familiar, Neohooking materials is a hyperelastic model that can define the material properties using just the shear modulus of the materials. And with that, you can compute, for example, the stresses as well as other quantities of relevance. So this structure is, this setup has a crack that's terminated at an interface that's allowed to have an incline angle that we can control. And there's elastic contrast across interface that's described by this value of S, which is the ratio of the shear modulus ahead of the crack tip and the shear modulus behind the crack tip. And so with this, we can also see that we can solve this problem analytically using finite deformation theory and asymptotic analysis by solving the boundary value problem. And we can find separable solutions where you have these P's and Q's, which are just loading depending on the loading of far field loading that can be calculated using extracted from finite element solutions. However, the important part is that there is this power, which is r raised to the nth power, which is a solution to the characteristic roots of the following equations that is dependent on the heterogeneity across the interface. So in this case, we can rescale this as in another parameter, which is alpha, just rescales this elastic contrast to a value between -1 and 1. And if alpha equals to 0, that means that there is no heterogeneity. And if alpha is to 1, that means it's infinitely stronger ahead of the crack. And so we can solve this characteristic root equation, and we can plot this n, right? So some of the results results of this is that for a homogeneous hyperelastic Neohooking material, the prediction is to have this power, which is 0.5. So this agrees with the theory where you have a crack tip essentially resembles a parabola. However, outside of really this area, no one has looked at these other effects of how heterogeneities affects at other incline angles. So what we're interested is to look at when phi equals to pi over 2, which means that the interface is perpendicular to the interface. You can see that as we sweep alpha, there's going to be a variety of this power law. So to look at this more closely, we have set up look at the crack tip solutions in both the terms of the cracked coordinates as well as stress solutions. So first, we can also set up a finite elements analysis in this particular format, where we can allow an incline interface where the crack is terminated at this interface. And we'll look at two particular cases where one, the interface is perpendicular to the crack, and another case, the interface is at 45 degrees angle at the crack. So here are some of the mesh geometries that we have generated at this crack tip. So first, we can look at the crack tip solutions of the coordinates of the crack tip. So we can calculate y1 and y2 of these separable solutions. So we can plot these solutions for the case when the crack is perpendicular to the interface for different heterogeneities from S equals 0.2. That means the material ahead is 5 times softer than the material behind the crack tip, all the way to S equals to 5. That means the material ahead of the crack is 5 times stiffer than the material behind the crack. So you can see that we can go from a significantly very, very smooth crack tip all the way to a very sharp and linearized crack tip in a very small amplitude. And this is the original crack. And first of all, I want to point out that our analytical solutions agree very well with the numerical results that could be extracted from the finite element solution. And secondly, so this solution also provides us these parameters, P1 and Q1 and P2, so on, that we can use to investigate other quantities as well. So if we look at, in the case of an incline crack, right, this crack is no longer symmetric. And we also have very good agreement for different heterogeneities in this case as well between the analytical and finite element results. So additionally, aside from the crack tip coordinates, we can also obtain the Cauchy stress, which is computed from just the first gradient of the solutions in the crack tip. And with this, we can calculate sigma 1,1 and sigma 1,2 and sigma 2,2 at any given point around the crack tip. So these we can calculate these G theta, GH theta, and H theta. These are deterministic solutions that could be obtained from our asymptotic analysis solutions. But what I want to point out is that we can know that there is a singularity of the stress. The dominant stress in this case, the sigma 2,2, has the singularity of 2n minus 2. So we can look closely at this, and we can first of all validate this again using finite element solutions. For different applied stretch in this case, you can see that we can very clearly see the singularity of these stresses. And additionally, if we look at this particular stress, dominant stress ahead of the crack tip, for different heterogeneities, we can also see clearly, first of all, the stress singularity. So what I want to point out in this plot is that increase of this heterogeneity, so increase of S, it leads to orders of magnitude of stress drops at the same distance ahead of the crack tip. So this qualitatively explains some of the toughening effect. If you look at a same distance ahead of the crack tip, for a material ahead to experience the same amount of stress, it will require much, much higher applied loading. So this qualitatively explains some of the toughening that we can see. And we also validate this results using experiments. So we fabricated a homogeneous PDMS in this case, and we can see clearly the homogeneous crack tip solutions that resembles a parabola. And if we plot, we fabricate a PDMS with an interface between soft and hard PDMS, we can see that this crack tip is much more linear, actually, very close to 1 in terms of this exponent. So if we plot this compared to the analytical solution of N that we have presented before, and we can see very good agreement in our the M extracted from crack tip opening compared to the solution. And we can also extract this N from the DIC of these. So that's what these speckles are for in these images. We can extract the coordinates around the crack tip, and we can also look at, you can extract this N from these DIC fields. We can also see very good agreements between these analytical solutions. So lastly, I want to also point out something we observed in this paper, where the inclined crack behavior, where the crack is at an inclined angle with the interface. And we observed something very interesting, where in the case of 45 degrees, we can see these cracks actually deflecting, almost propagating downwards after it reaches the interface. And at the case of, in this case, 60 degrees, we also see these deflections. We all actually see this all the way up to 75 degrees, that where the crack also deflects along this interface. But at the case when the crack is perpendicular to the interface, there is a penetration that happens. So we really actually wasn't even able to understand why this is happening, but this is obviously a very interesting phenomena that's worth of future investigation. So lastly, just want to talk about quantitatively, we can also know this toughening effect between this dissimilar Neohooking materials. And we can do so by invoking a fracture criterion, which is looking at the principal stretch. So we can compute the principal stretch at a given material point ahead of the crack, And we can compute that, and it can relate it to a critical stretch that is a material characteristic. And the criterion indicates that for the fracture to occur, it needs to, for the principal stretch ahead of the crack at a certain critical length scale, RC, to reach this critical stretch. And we can calibrate this criterion using finite element solutions, and we can find out that this critical stretch is around 13 or so for this materials. And we can find out this critical stretch, applied stretch for different heterogeneity. So we can plot this on the left plot here. It shows that we can have a quantitative prediction for this applied critical stretch, which is again related to the toughness of these materials. Okay, so now I'll move on to the second part of my talk. The first part, I talk about the effect of material heterogeneity, but I also want to point out that we can create toughness by using only geometry as well. So this work is really inspired by what's called a Borigan structures. So this is found in the dactyl club of mantis shrimp, where they have these helicoidal fibrous structures that represents in this helical fashions, where the fibers has a pitch angle as you move up in the layers. And this work has been previously replicated using multi-material printing, creating these fibrous structures and creating what's called a twisting crack, and leading to very high failure resistance of these materials. But our idea is to use utilize defects that's generated in 3D printing, specifically geometric defects, as well as material heterogeneities due to cooling and heating of these filaments during 3D printing. And the result of this is that you can see that there are these geometric pores very nicely aligning between the filaments. And the result of this is that there is an anisotropy in the strength. If you pull this materials printed in the direction of the filaments, it will be much stronger compared to in the direction that's perpendicular to the filaments, which is in this direction and this direction, right, due to these defects. And the idea here is now we can program these defects by programming the infill layers similar to a Borigan structure. So essentially how we can do this is that each layer is moving up this direction. We change the infill angles with a pitch angle, which is defined by this gamma, right? So there's a change of the angle as we increase up the layers. And we test these materials in a 3-point bending setup, which is indicated here. And the first layer has a infill angle that is preferable for the crack to propagate in between the filaments. So it's actually the weakest point in the first layer. So here are some crack tip images during a 3-point bending. And you can see that in the case of pitch angle 5 and 10 degrees, we have these highly intricate surface damages, which resembles the twisting crack that is observed in these materials. And if we look at the low displacement curve, we can compare that with some of the control samples, right? So for example, if we have this phi 0 equals to 0, but there's no pitch angle, this material is very weak because the crack just propagates straight through the defect, the region, and fails very quickly. And we can also compare that with if the case of phi 0 is 90 degrees, where now the crack is the strongest for the crack to propagate. And this material is very, very strong. So with a very high peak load, but it also fails brittly, right? So as soon as the crack propagates, it propagates through entire structures lose this the capability to carry load. However, for the material with these Borigan structures, these defects arranged in this Borigan structure, we have very, very high resilient to crack propagations, where you can actually load this material all the way to the 3-point bending fixture, where we can no longer load it further. So this shows that these structures are very resilient. The crack doesn't propagate very catastrophically in these materials. We also investigated the effective printing parameters to really understand how they can affect these structures. So we have these geometric defects, and there are ways that in a lot of these 3D printing communities, they want to get rid of these defects, right? For example, one way to do so is by annealing. So you can heat this material very close to its glass transition temperature, where now these plastic will sort of melt, but still hold its structure, and you can essentially close these pores. So if we take these structures with different pitch angles, and we can see that such annealing does help the fracture toughness. That means that the material gets stronger. However, the energy dissipation, which is the area under the stress, the load displacement curve, shows a decreasing effect. By annealing this material, we do not see an improvement in the energy dissipation at all. In terms of, in fact, this material becomes actually more brittle because you're closing up these pores. And similarly, we can also look at the effect of these filament spacing. So for the structures that we have printed before, it all has a filament spacing of 0.3 millimeters. And if we have a smaller filament spacing, that means the geometric defects will become smaller and smaller. So you can see that there is a positive correlation in the fracture toughness. We have a smaller filament spacing, then the fracture toughness will be larger. However, this is not monotonic in the energy dissipation. It turns out that the filament spacing that we're using, the 3.3 millimeter, is actually the best one that leads to the highest amount of energy dissipation. And next, we can also look at mechanistically the origin of these resilience of crack propagations. And there are a lot of work that in this space prior to understand these natural composites of this twisting crack. And this twisting crack can be defined using a few geometric parameters. So if you can look at this capital X, Y, Z, which is the global coordinates, and you can describe this twisting crack using a local coordinates that rotates along this crack tip with the help of these two angles, alpha and phi. So you can actually define the whole twisting crack surface with a twisting angle that can be defined from this pitch angle as well as the distance of subsequent layers. And there are analyses that can compute local stress intensity factors in different modes in K1, K2, and K3 as a relative to the global loading parameters. So however, there hasn't been a counting of a different modes that's happening in these materials. So what we have observed that there is actually two types of loading of the deformation of crack propagation. So first is called a twisting mode. So this means that the crack will follows the weakest point as it propagates through the structures, and it follows these defected areas. However, at some point, this is no longer favorable. For example, if the crack reaches a layer that is perpendicular to the crack direction, and this will lead to an activation, what's called the branching mode, where now you will require breaking of these filaments. So these are the two competing modes that can be used, a mixed mode criterion that we introduced, and we can compute the relation between the applied energy release rate and the local energy release rate that's experienced by the structure. So we can compute this, and we can plot in the surface plot. So the blue surface plot is actually when we do not account for this mixed mode fracture. So you can see that having these mixed mode fracture actually increases this ratio of G0 over G1, which means that a less load is required for the cracks to propagate. And another effect that we also observe is that as the increasing phi means that the crack is further away from the initial crack tip. So this means that having as the crack moves away, it will require additional loading for the crack to propagate. That also explains some of these increasing high failure resistance that we have observed. And with this particular model, we can also plot the contribution coming from the twisting as a function of the G naught. And you can see that initially, when the crack is very close to the crack tip, most of the contribution comes from twisting mode. And as it moves forward, more and more it's going to come in from branching modes to a point where most of the energy and most of the contribution will come from the branching mode. So we can also validate this microstructurally. And one way to look at this is look at the surface damage, which is cross-section post fracture. And we can observe that for these various twisting angles, we can first of all see a periodicity of the crack tip. So in this case, this structure has a total of 2 periods when the case of pitch angle is to 5 degrees, and 4 total period of 10 degrees, and much more for the other cases. And additionally, we can also observe regions of twisting crack propagation, which is indicated by, you can see these subsequent very nice layers of twist of these helical crack pattern. And then at some point, there is a change of the mode into the branching. You can see that there's actual breaking of these filaments, and then followed by twisting and branching again. It's also very obvious in the 10-degree cases. You can see these twisting, branching modes. So you can see that our model actually very well predicted. You can at the beginning you have these large twisting, and then it goes into branching, and then eventually it has to after one period it goes back to twisting and branching again. In addition to surface damage, we can also look at microstructural damages. So in this case, we actually loaded 6 separate samples all the way to different displacement, and we halted the test, and then we put into a micro CT. And what we're interested in this particular is this YZ plane, which is this plane, we can sweep it across the crack direction as we move through the samples. So here are the 3D rendering of the microstructure. So you can see in the beginning, this is the first sample, which is when the cracks start to propagate, and then increasing propagation through the structures, where you can see very large damage in the very end. So we can, in addition to damages, we can also measure very accurately the crack length, and we can use this very nice method that's introduced by Ritchie, where we can calculate the energy release rate as a function of the crack growth rate. We can also see this bilinear regime, which is observed in a lot of natural composites where there is increasing required loading for the crack to propagate through the structure. So first, we can look at in the first stage where the crack just propagate into the structures, and you can see that there is damage occurring along these defects. So in the first few layers of the structures. And then as we propagate in the second structures, you can see that the first layer is fully cracked. And however, if you move into the structure, you can see there is a mixed mode fracture where there is twisting happening along the edges of the structure. However, there's branching, where it's the breaking of the filaments as you go into the center of the structure. And this is also observed in later structures where there's competing factors of fracture in the twisting mode and branching mode. And more and so on in the later stages, there's actually a change of mode of fracture where you pull these filaments, the filaments become more and more aligned in the loading direction, and you're pulling away these remaining filaments because of these plastic in general is inherently is very stretchable. This also explains somewhat of this change of the slope, where there's a different there's a different failure mechanism that competed at here. So lastly, I will talk about there's also some ways to optimize the structures. And this increasing the failure characteristic is also coming at a cost, where if we look at the structure with a homogeneous no Borigan structure, has a very high fracture toughness. However, by having these Borigan structure, you sacrifice some of these fracture toughness. But in return, you get a much higher energy dissipation throughout the entire three-pending process. So there's this competing factor of fracture toughness versus energy dissipation. And if we look at nature, right, so in this case, in dactyl clubs, it's actually a combination of these regions. So there is an impact region with a high modulus, and then followed by this periodic region with this periodic modulus that can stop the crack propagation. So in this case, we have an idea of generating a unidirectional region, which mimics this impact region with high strength structure, which is aligning in the highest strength direction, and followed by a periodic region where we have these Borigan structure. So in return, we can have the structure within this heterogeneous arrangement of these defects. We can obtain fracture toughness of in between of the control samples, as well as energy dissipation of in between of these control samples. So there is some tunabilities that we can also look at to obtain fracture toughness and energy dissipation simultaneously. So to summarize, I want to point out that when designing these tough materials, there is both two methods to create toughness. One is through material heterogeneity, and one is through geometric heterogeneities. And these two can sometimes come hand in hand, can further improve the toughness of architecture materials. With that, I'll acknowledge my advisor, and as well as Professor Raney, as well as Professor John Bassani for the help in the first part, and some of the funding agency. And feel free to follow me on Twitters as well. I think this is an important platform for us to share our research as well. And thank you for your time, and I'll take questions from anyone who is interested.